6. This is about exponential functions. Now, exponential function, I said that, a subtopic will be logarithmic, which I won't talk about today. So I'm going to leave that for now. Really start out very simple general form. Is that y is equal to a times b to the x. Very, very simple. All we're talking about is this thing. But this thing turns out to be incredibly useful, incredibly powerful in the way we think about our world. We're talking about pandemics, we're talking about virus spreading. The exponential growth of virus is following this equation. The exponential growth of population is following this equation. The money that you put in a bank or put in a stock market is following in this equation. The value of the home that you live in, if you are fortunate to actually own, your family own a home, your home value growth is following this equation. If you somehow, a terrible case, we are in a nuclear holocaust, and then a place gets bombed by a nuclear bomb, and we have radiation in that land, and you want to figure out at what point you're able to get back to that piece of land when it is safe without radiation, it is following this equation. It's pretty crazy, right? So now let's start with exponential growth. So on this side is growth. On this side is decay. They are the same thing, right? The two sides of the same coin. Take a look at one, whether it's virus, maybe do it this way, spread of the virus. The spread of virus. Let me see, what should I use? I'll use time, maybe not time. Maybe I'll start with people, P, and then infections. So this is infection. When there is nobody, zero, in a zero condition, there is one virus, and then that doesn't make sense. That doesn't make sense. Let me we think about the problem setup. Let me do it this way. Instead of people, just do time. I'm going to do time. T. Time T. And maybe just infection, or maybe virus count. Virus count. Okay. When there is no time has elapsed, there's one virus in our system, in our population. When whatever the next time that you counted, one virus has infected 2 people. Next time you counted, how many people do you think will get infected? 3 people? 4 people, right? Because one person can infect another person, right? If one virus infects 2 people, then 2 people, one of the 2 will infect 2, the other one will also infect 2. So that means how many infections in total? 4. 4 infections. What's that? Right, so 1 to 2, right? and 2 to 4, right? 1, 2, 4. And what do you think the next one is going to be? Huh? 6? How many? 8. 8. Right? And then the next one is? Huh? 16. Yeah, 16, right? So it goes more, right? 6. 1, 2, 4, 8, and then 16. Right? So it's a spread, and it's a exponential growth. Now, if you take a look at it, for every single number, it is multiplying by 2, right? 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So you have this exponential growth. So the question then here is to say, well, what happened when you get to 100? Then what number would this be? Right? That's the question that we want to solve. That's the question we want to solve. So I'm going to try to do the solution here using this model. Okay? Yeah.
And so the model is time is x.
That's right. That's right. Time is x. So x we turn that into t, and then y is our I. Right? Yeah.
And b is the rate of infection.
B is the rate of infection. It's possible. We don't know yet. Well, I haven't told you yet. So we're going to discover. We're going to try to think through it and see, well, what will A be? Right? What will A be, and what would the B? What the value for B is? Because we need to be able to come out with the correct A and correct B. Then we will have an equation. Then we can plug the 100 into the t, right? So here, let me, I'll get to you. So if we simply rewrite this, then we will say our workable equation at the moment, what we're attempting to use this equation is, we want the equation of I equal to A times B to the t. Okay. So if I want to find this answer right here, right? This answer right here, then we want 100 to go where? This 100 go where? To t, isn't it? And then we want this answer to be represented by the I, right? Number of infections. When t is equal to 100, what would the number of infections be? That's what we want. But we know that we haven't figured out A and B. If we don't know what A and B's are, then we wouldn't be able, we will end up with unknown, unknown, and unknown, 3 unknowns in one equation that would make sense, right? So we want to be able to figure out what A and B first. Then we want to know what they are first before we apply the equation with this setting right here. So how do I find A and B in this case? Right? So here's the equation, but the problem with this equation is it's not workable. It's not useful to us because we don't know what this is, and we don't know what this is. But if we do know what these two are, then we can apply the data and to find the missing one, right? When t is equal to 100, we want to find what I is. But if that is only if we know what A and B, what the values for A and B. So right now we need to find A and B. How do we find A and B? Well, you are lucky because you have all these numbers in front of you. You can simply pick, right? We have 2 unknowns. We can take a section or portion, whether it's here or anywhere else from this data set, and we can apply it to find A and B. So let's take the first set of data. T equal to 0, I is equal to 1. So if T is equal to 0, right, so 0, 1, then 1 goes to where? Goes to I. So it's 1 equal to, do we know A? No. Do we know B? No. Do we know T? 0. Right? We know T is equal to 0. So we solve for this. So 1 is equal to A times, well, anything to the 0 is 1. So that means A is equal to 1. Oh, at least I solved for A. So I got A. So now I can rewrite this equation again. I have I is equal to 1 times B to the T power. Now I still don't know what B is. I still don't know what B is. So I can use the second set, 1 and 2. So 1 and 2. Okay. Put it back in here. So I is 2. 1 is 1. B we don't know. T is equal to 1. B is equal to 1. Oh, so B is equal to 1 is just B. B times 1 is still B, so B is equal to 2. Therefore, now in math, dot, dot, dot means 0, 4, right? Dot, dot, dot. So the triangle dots. Therefore, B is equal to 2. So what does that mean? That means I'm going to erase the exponential decay. I'm going to eventually move it over on this side. So what does that mean? That means my equation is finally equal to y is equal to A is 1 times 2 to the t. 2 to the t. Yeah? That makes sense, right? That makes sense, right? I mean, you actually don't have to write 1 times 1 here because 1 is pretty obvious. 1 times anything is itself. So it's just I is equal to 2 to the t power. That makes sense because 2, like any number you put in there is the exponent of 2, right? So when t is equal to 1 is 2 to the 1 power. When t is equal to is 2 to the second power, which is 2 squared, which is 4. If this is 3, this 2 to the third power, which is 2 times 2 times 2, 3 times. So in this case, right, so if we want to solve for when t is equal to 100, what is I? Well, then not just I equal to 2 to the 100 power. Right? And that's the answer. That's the answer. Do we need to know what it is? I mean, you can use your calculator. 2 multiply itself 100 times.
I get an error.
Yeah, it's 1.267 times 10 to the 30 power. Times 10 to the 30 power. What does that mean? Does anybody know what that means? Yeah.
It's that number multiplied by it's in
1267. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. 28, 29, 30. That's the answer.
We forgot the commas.
What's that?
We forgot the commas.
Oh, yeah. I won't worry about that. It's just a big number, right? It's just a big number. So when you have a virus infections, without curbing that, and it just continue to double, double. You do 100 times, that's how many infections there are. That's one of the reasons why coronavirus is so hard to stop, especially when it's dealing with the severity. There you go. Now, but here the point is, this is an exponential function, right? Even though it's t and I, you can think of it as x and y. It doesn't really matter what letter you use, as long as the form matches this, right? And you can see that it's taking on this number as a base number, and then basically multiply itself based on the exponential value. That is the problem, right? Now let's talk about exponential decay. So I'm going to move this over here so I can see the board here. Exponential decay. Now, exponential decay, you may have learned from your chemistry class. I don't know if you did, hopefully you did. But the idea of radiation. Earlier I used the nuclear holocaust as an example. It's not so far-fetched from reality. When the atomic bomb was dropped in Hiroshima, that whole section of a 30-mile radius was filled with radiation that would cause cancers and so on and so forth. Yeah.
I think a better example might be the nuclear reactor that fell down in Japan.
That's closer in history. Yes. Regardless, whichever a location where you have a nuclear radiation, the chemical, the uranium isotopes. Have you heard of that name? That term from chemistry, isotopes. It has a half-life. They have a half-life of 30 years. 30 years. What does that mean by half-life of 30 years? Here's someone, yeah.
It takes 30 years for it to decay only half of it.
Right. It will drain, right? The amount of radiation will drain out, but only drain out. Not think of it this way: it's not like a bucket of water with a hole on the bottom, and you would drain the water and it just drains out in a certain rate that can be calculated using calculus. But the radiation doesn't drain out that way. The radiation drained out by the multiple of half. By the multiple of half. So it's like you have this much, then the next unit of time will be half of it. Next unit of time will be half of half of it, and half of it, and you keep doing half of it. Will you ever be able to get rid of radiation? You're always going to have a trace of radiation, right? Because eventually you're going to get onto the asymptote, right? You'll never get to zero, but you'll get closer and closer to zero, but never zero. So in this case, for example, time and the amount of radiation. So say, for example, at time equal to zero, we have, say, 100 units of radiation. Let's just call it units, whatever that means, 100 units of radiation. So if we say radiation half-life is 30 years, that means the next unit measure is 30 years later. And 30 years later, whatever the 100 units of radiation, you end up with how much? 50, right? 50 units. And then after 30 years, you do another 30 years, that would be 60 years. And after 60 years, how much? 25, right? 25. What's that?
And so it just keeps going down, but it never gets anywhere to zero.
That's right. That's
But
right.
actually, the radiation might be untraceable.
Untraceable because of technology.
Yeah.
But in reality, it is still a trace, right, somewhere. Now, so this one, if you graphically speaking, if you look at it on the graph, at time equal to 0, so this is time, and this is radiation units. Time equal to 0, we got, say, 100 units right here. And then 30 years later, is half of it, which is 50, so we put a dot right here. And then, so if you go to 60, it's 25, so half of the 50, so you get 25. And then we can basically extrapolate and say, okay, then that means 90 years later is half of 25, which is, what is it? 12.5?
I think so.
So it's like right here, right? And then 120 years later, it's half of 12.5, so 6.25. So as you can see, this graph will look like this. This is the exponential decay. Decay problem. Now over here, I forgot to draw this picture graph out. If we draw this graph over here, this graph will be, so it's 0 at x equal to, or t and I, 0 is right here. 0 will have 1, and at 1 we got 2, and at 2 we got 1, 2, 3, 4, and over here, 3 we end up with 8, which is double in size, so you end up with something like this. Now, obviously, you can imagine on the other side, which is going this direction. Yeah.
Do any of the exponential problems ever reach 0?
No. No. So that's in fact remember we were learning about asymptotes and the range, right? The ideal range. Really it came out a lot of studies, whether it's in physics or biology. Is this concept, the logical concept, leads to the idea of asymptote, meaning that it's a line that you keep chasing and you get closer and closer, but you can never get there, right? And that's really a powerful idea, because I think we human brain likes to think that when you get closer to something, you get closer to a point where you get there. But it is possible that you keep chasing something, you can get closer, but never get there. That's the paradox, right? It's a conceptual paradox. So philosophers like to take these mathematical concepts and kind of apply to bigger philosophical discussions. Anyway, let's go back to math here. So here we use the same thing, right? We use the same model. Y is equal to A, B, X. So I want you to find the specific, what we call the particular equation. Find a particular equation for this case. In the math test or problem assignments that you have, whenever they say find a particular equation, that means it's taking this, what we call the general equation. This is a general equation, and figure out the specific value for the case that you're studying, that you're looking at, and that would be the particular equation. So this is a particular equation over here. This is a general equation. So find a particular equation, which means figure out the A and B specifically for this. So go ahead. I'll give you a head start, and I'll come around and go there. Similar to this, right? Similar to this. Now, by the way, if you look at this, this is times 1/2, right? Times 1/2. Notice I always use multiplication, I didn't use division. Because I want to keep it consistent. It's about multiplying. So go ahead, find A and B for this case. Radiation decay. I'm seeing some challenges. Kind of I'm seeing the pattern where a lot of people kind of get bumped up against, but some of you actually did pretty well, so I'm very, very proud of you. So in this case, right, this is the general equation. We can rewrite this general equation, right, using the letters that we have over here. We can call this R is equal to A times B to the T. All right. Now remember, we need to figure out what A is and what B is. We have no idea what they are, but we have the data to help us. 0 and 100. 0 and 100. 0 goes to T, 100 goes to R, so it's 100 equal to A times B to the 0 power. Now, anything to the 0 power is what?
0.
Anything to the 0 power is 1, right? So, you end up with 100 is equal to A times 1, which means A is equal to 100. Okay, so that's nice. That's nice to know. So now we can write the next one now, right? We can rewrite this a little bit differently. R is equal to 100 times B to the T, but we're still missing the B, right? And that's why we need a second equation. We need another set, right? If you have two unknowns, you need two equations to solve it. If you only have one unknown, you only need one equation to solve it. If you have three unknown, you need three equations to solve it, right? That's logical. So in this case, we need another one, so we use 30 and 50. 30 and 50, right? R in this case is 50, so 50 is equal to 100. B, we don't know. T in this case is 30. Now, this is 100 times B to the 30th power. I want to isolate B to the 30th power, and this is multiplication, so I will divide both sides by 100. Right? I will divide both sides by 100.
Alternatively, you could simply just ask yourself what to the 30th power is equal to 1.
Yeah, right. That's right. Sure. But what I want to do is step by step so most people can track with this, right? So I do that. So I end up with 1/2, right? 1/2 is equal to B to the 30th power. Okay, so you got there. Now, this 1/2 is equal to B to the 30th power. Now remember, if this would have been B squared, you would square root on both sides. If this is B cubed, you will cube root on both sides. If this is 30th power, then you will be 30th root on both sides. Right? So you will do 30th root on the 1/2 is equal to B. You say, well, what is 30th root? Well, it's 1/2 to the 1/30th power. Now you can use your calculator for that. You can put 0.5 to the 30th power, 1/30th. So I will put in the calculator. This is what I will put in the calculator. I will put 0.5 to the parentheses 1/30th. This is what I will put in the calculator. Okay? 0.5 to the power of parentheses 1/30. So then UB is 0.997, no, 0.977. 0.977 dot. They're bunch numbers. Now, by the way, exponential function is super sensitive to little adjustment. So if you drop certain numbers or round certain numbers, it will drastically change your outcome. And so I would tend to just use dot without rounding to signal that it is actually quite decimal sensitive. So then with my final equation, bring it all back together, R is equal to, A is 100, B is 0.977 dot, parenthesis to the T power. This is my particular equation. Okay? Got it? If you look at some of these problems that we have, right, I gave you two examples to start, a teaser questions. Both of them start with the first value that has a 0 in there. Notice that? And then whatever the starting point right there, it turns out that that number ends up right here. That number turns out to be the A. So oftentimes, when you have y is equal to a times b to the x, this A, we usually call this an initial condition or initial value. You remember the first example I gave you, right? The initial condition was 1, so A was 1 for that first problem. The second problem, the initial condition is 100, so A turns out to be 100. But a lot of the times when you are not given that case, you're not given what the initial value is. So let me see if you have this, right? So now we have P is equal to 70,446 times P to the T power. Then we're going to use the next value, which is 10 and 1,305,600. So we have 1,305,600 is equal to 70,446 times b to the 10th power. Then divide both sides by 70,446. You got 1,305,600 over 70,446 is equal to b to the 10th power. So b to the 10th power, so if b to the 10th power is that means b is equal to that whole thing, 1,305,600 divided by 70,446 to the power of 1/10. Did I lose anybody? This is the 10th power, right? So you want to get rid of 10th power, you do 10th root, right? 10th root on both sides. That means taking this whole thing to the 10th root. 10th root means it's the power of 1/10. Yeah?
So in the calculator, right? In the calculator, you can go ahead and just do that. Calculator, you do 1305600 slash 7446 parentheses to the power parentheses 1/10 parentheses. That should give you a number. I'll use, what do you have?
The number that it is 1.33904.
1.33904. Is that what you have? How many of you have the same number? You confirm it? Confirm it? It's not, huh? Maybe you can type it out later.
Yeah.
That's not it?
What he did, instead of re-entering the number manually, he just continued typing the problem and used the answer.
Oh, I see. I'm sure there's probably decimal, but it doesn't really matter. We can just maybe drop it right here. Okay, how about dropping it right here? Let's just do it this way. So your answer, right? Your final conclusion is P is equal to 70,446 times 1.339 to the T. Now here is very interesting idea. When you look at the B, you take that B value and you subtract 1. Whatever that remaining numbers, the number subtract 1, this number subtract 1, turns out is the rate of increase. So what that means is that this home is increasing at a 33% a year growth. This house is raising value by 33% a year. Your stock market at best only gets you 10%. Your savings account is point something. Don't even worry about the savings account, so it's useless. Put your money in savings account is actually decreasing value every year. If you put it under a mattress, it's pretty bad too. So you know what I'm saying? Like it won't catch up with the inflation rate. Right? So here is we're talking about the Bay Area housing are increasing at 33% value for the last 10, 20 years. Right here. Now, one place I will show you, and I know I'm probably out of time to show you, and I don't know if Mr. Chen is able to show. If you have this calculator, I'm going to show you something real quick. Okay, because you can take advantage of this. On this calculator, you'll see a button right next to the left arrow. It says stat. S-T-A-T, stat. When you press stat, it gives you a menu of options. When you press stat, it gives you a menu of options. You select the first one, which is called edit, and it gives you a bunch of lists. List 1, list 2, list 3, list 4. So what you can do is you can put 0, 10, and 14 in list 1. 0, 10, and 14 in list 1. And you can put these value 70, 446, 1305, 600, 180000 in list 2. You can put those values in list 1 and list 2. this is kind of like a table. Once you're ready, here's what you do. You press stat again. You press the stat button again. Press stat button again. And then you arrow to calculate. You arrow to calculate. And now calculate gonna give you a bunch of options. On the screen, it only show you 9 options. You can arrow down further. Option. That's right. Option 10 says exponential regression. EXPREG. Exponential regression. You press enter, and you want to make sure X list is list 1, Y list is list 2, and then you arrow all the way to calculate, and you press calculate, boom. Here it gives you the A value and B value. Now it's a little different from ours because we only take the 2 data points. We take this data point and that data point. Your calculator took the 3rd data point and map it into an even more accurate equation for you. So your calculator can do all this. What's that? Now this is wrong in the sense that we didn't consider the 3rd data point. This calculator takes 3 data points and map an even more accurate equation. Okay?
Thank you.
Have a good day. Good day.